purpose of this video is to familiarize you with the conventions of drawing two-dimensional and also creating three-dimensional views of magnetic and electric fields. So let's start with magnetic, and we'll start with the two-dimensional views. Usually you're more familiar with this. Here's a bar magnet, and we usually model it as having a definite north and a definite south pole. And based on the nature of magnets, this is it's a relatively common model, and here's why. So on the small scale, these materials are actually oriented all relatively in one direction, depending on the strength of the magnetic field that created this. How they're oriented could be more or less aligned. But if you have a pole which we call north and have a pole which we call south, then there's actually a convention here that shows us if we were to have another north pole, let's say a test pole. If I draw that out for you here. So there's a whole magnet here, but we're only bringing the north pole nearby, just as an example. Then what would the force between the two look like? How strong would it be, and in what direction? So the strength is determined by how close they are. The closer it is, the stronger that force is. The direction, it depends on the sign, really. So north with north, it would be the polarity, and since they're like polarities, then they repel. Opposites attract, likes repel. So what would happen in this case is you would have a strong repulsive force in this direction. But with field lines, we don't make the arrows bigger to show that they're stronger. We don't really make them longer to show that they're stronger. Instead, we draw a large number of them, and the closer together they are, meaning the more that there are in that square section, the stronger it is. So if I take this north portion of a full magnet and I move it closer, then you see that the force would be stronger because it's actually a higher concentration of lines. If you just have this dipole, this full bar magnet here, if you have it alone by itself, then what you end up with are some really symmetric field lines. So I'll draw this a little bit more freehand just to give you an idea. And you see again, the further out you get, and even the further away you get from the strongest ends of these magnets, not perfect here. But when you do that, you actually get a higher concentration near the ends. And if you do this in the presence of, say, iron filings, then you really see this strength, because the net forces tend to go towards zero at certain points in the magnetic fields. So if you have a north pole here that comes close, say you have another north-south bar magnet, comes here, then a higher concentration, out here further away, lower concentration, and again, more towards these edges, you'd have the higher concentration. That means it's the higher force. And technically, you'd have them repelling in this direction. So you could draw arrows all the way along. So the convention is that we draw these field lines from north to south, because we're literally saying, at this point, what direction would the force have? And we could, again, from the densities of these lines, these imaginary models, we would be able to tell you the strength as well. So you could draw this on every one. Now, when you talk about the electric fields, we generally talk about objects that have some charge. We model them as little spheres. And we especially, it makes it really nice to model them as spheres that have no real diameter. Makes it a lot simpler for us. The convention here is that you take some positive test charge, and we're not bound by the problems of having to have a north and a south here. We're not bound by that. We can have something that is overall positive and something that's overall negative and still be its own unique particle. You take a positive test charge, and where would the forces be acting, in what direction, and how strong? How strong is, again, the same thing, the concentration of lines, and the direction is determined by not polarity this time, but really sign. So positives and positives, oh, it's going to want to repel. The force is going to be away from this and acting on the test charge. In this case, positive and negative, they are dissimilar, and so it's going to be an attractive force. So if we draw the field lines, let me just separate these by some large distance. Draw the field lines with the positive. If I'm here, what's the direction going to be? It's going to be repulsive. Okay. If I move the test charge here, what's the direction going to be? Same thing, repulsive. And it end up being the same all the way around. And for your sakes, I'm going to draw some of these in. You can draw as many as you want. The lengths of the arrows don't really matter. Technically, you could bring them out very, very far. What really matters is recognizing, again, the direction and the concentration. So here I am. If I come further out, okay, I might only be hitting, according to this image, one field line. I come in closer, maybe I'm hitting double the field lines. But again, a more precise model, there is a much more uniform distribution of these lines. But you get the idea. If you're interested in the exact mathematics, that's Coulomb's law. It follows the inverse square law. So if I start out here, I have a certain amount of force, and if I come in half as far, it's not twice as strong of a repulsion, it's actually 4 times as strong. If I came in and I have covered 2/3 of the distance, then it's actually not 3 times stronger of a repulsion, it's 9 times stronger at that point. For the negative side, you say to yourself, here's my positive test charge, just some imaginary charge I bring through. What direction is the force going to act? It's going to be an attractive force, so be downwards or inwards from the perspective of the negatively charged particle here. And again, same thing, you can draw this a lot more neatly possibly if you took the time to do it. There are plenty of online simulations which model these expertly. You can draw any number of uniformly distributed field lines you like, whatever makes sense for your situation. And again, in this case, here I am. If I come closer, if I pull my test charge closer, then I have increased it by the inverse square. So here I am. I cover half the distance. I'm now 4 times as attracted, not just twice as attracted. So that's 2D modeling. If you bring these together, get something very elegant. Just kind of connect the dots. There's more to it than that. Not perfect here. And we can get stronger, weaker. Well, I think you get the idea. Again, there are online simulations that do this much better than I do. These go out to infinity in this little environment. And you say, okay, here I am. I've got this little system now of positive charge and negative charge. Very weak out here because the concentration of field lines is weaker. Follows, again, Coulomb's law for these charges. Attracted in this direction. I could draw the arrows as I needed to. And you actually, let's say that I'm right here. What's going to happen? Well, I'm going to move along in this direction. At this moment, I have a force acting on me along the field line, tangent to the field line. So tangent to this field line would be a direct attraction. Tangent to this field line would be a direct repulsion. At any one of these points, oh, here we are, getting repulsed. That's the idea of 2D modeling, and it can get as complex as you'd like it to. But when we really want to get into this, we talk about 3D modeling, and it gives us a whole other view. So this, if you look at the calculation, is actually applying Coulomb's law, that inverse square law applied to charges. And I have three little sections here where I have it programmed in where I can model these charges. And if I change one value, let's say I give it a value of 3. So this could be coulombs or any unit of charge that you'd like, any microcoulombs or nanocoulombs, anything that you'd like. And I give it one value. First of all, just to show you the 3D model of it, it's a flat plane. But if I give it a value, it recalculates this charge space here, right? It recalculates really the electric fields. And it models it. So let's say that we take our positive test charge. With that positive test charge, if I'm right here, I'm going to want to roll down. Imagine like a gravitation. Imagine this is like a hill. I want to roll down. I'm actually being repulsed. And the steeper the hill, the greater the repulsion. So if I start here, I'm repulsed less. Here I am here. The force is less. As I go down, the force is actually less and less and less. Now, let's choose the same but negative value. The numbers here actually almost give you a hint of what happens. You can see that valley. Won't let me actually turn it. But you can see that valley there. It actually is, let me get rid of the 3 there. It actually is a little valley. So if I take my positive test charge, what's going to happen? Well, the force of attraction is not much. But then as it gets steeper and steeper and steeper, the force of attraction, that distance away from this negative charge particle, is actually greater, much, much greater. Again, by the inverse square law for charges known as Coulomb's law. So you can manipulate these however you want. And you get a really good idea of what these electric field lines look like, but instead of lines now, it really is a 3D topography. So hopefully that helped you understand E fields, meaning electric fields, and some more on B fields, meaning those magnetic fields. And depending on what your mind prefers, you can actually use this model for 3D or 2D. Some people like the lines better on 2D. Some people really appreciate this topography. So I'll leave that up to you. Have a good one.